We have discussed in the last lecture about various factors in operating system design, basic functions of operating system, various processor modes, system call and system programs. There are two views of processes, the programmer view and the system view. In this lecture, we will discuss the system view of process and resources. System view of the process. A process is an instance of a program in execution. We can say that the specific instance of a program execution is synonymous with that process. An intention to activate an executable program is announced to the operating system. The operating system responds by creating a process and brings the required program and data into the main memory. In general, this activity consists of creation and initialization of operating system data structures for monitoring and controlling the progress of the related process. The process is allocated some part of the main memory to hold its program and data. Once created, a process becomes active and eligible to compete for system resources such as processor and input output devices. The operating system allocates various resources to the process as the program execution evolves. The execution context of the process consists of this resource allocation information, the current state of the program execution, the instruction that is to be executed next and other information related to the program execution. In short, the operating system uses a process as a handle to manage one program execution. One system may have multiple processes running simultaneously. These processes can be of two types. First, a collection of dedicated processes to carry out various operating system specific tasks. These processes execute only operating system programs and neither the utilities nor the user applications. They are referred to as operating system processes or kernel processes. Second, the remaining processes in the system are referred to as user processes or application processes. User processes execute utilities and application programs. All the processes can potentially execute concurrently with the CPU multiplexed among them. By switching the CPU between processes, the operating system can make the computer system more productive. Out of these multiple concurrent processes, few may be executing their input output operations, one may be served by CPU and few may be waiting for their turn to get CPU as shown in figure containing two processes. We can discuss this with an example. Let a person is going to bake a cake. He has cake recipe and a kitchen consisting of necessary items like flour, eggs, sugar, extract of vanilla and so on. Here the recipe is the program, the person is the processor and ingredients are input data. The process is the activity consisting of our baker reading recipe, fetching the ingredients and baking the cake. In the meantime, the son of the person comes crying saying that he has been stung by a bee. The person records where he was in the recipe, gets out a first aid book and begins following the directions in it. Here the processor has been switched to another high priority process having different program. When the bee stung has been taken care of, the person goes back to his cake program, continuing it at the point where he left off. As we have discussed that one system may have multiple processes running simultaneously, conceptually each process has its own virtual CPU. In reality, of course, the real CPU switches back and forth from process to process. In operating system view of process, we discuss how operating system creates processes, how it keeps track of process states, and how it uses the process states information to organize execution of programs. It also includes monitoring of all the processes and looking at what each process is doing at any moment of time, whether executing on CPU, waiting for the CPU to be allocated to it, or waiting for an input output operation. During its life, a process may be in many states as discussed below. Process states. There are 5 process states, namely new, running, waiting, ready and terminated as shown in figure. Initially, all processes reside in the new state. When the operating system receives a process creation request, it creates a new process by allocating a descriptor from the pool of unused process descriptor objects. The new process changes its state to ready state and the system builds up the initial execution context. All the processes waiting for their turn to get CPU are placed in ready state. Ready state is implemented as a queue containing all processes waiting for CPU. This queue is called ready queue. When CPU becomes free, one process from ready queue is allocated to CPU for execution, changing its state to running state. The running state means that the process has all the resources it needs for execution and it has been given permission by the operating system to use the processor. Only one process can be in the running state at any given time. There are 3 alternative transitions from running state. First, from running state a process may terminate if it completes or operating system aborts it and enters to terminated state. When a process enters the terminated state, the operating system cleans up the process and releases all the resources acquired by the process. Second, the process in running state may require some input output operation and it moves to waiting state. Waiting state, also called block state, contains all the processes waiting to complete their input output operations or performing their input output operations. Waiting state can be implemented as multiple queues, separate queue for each input output resource called waiting queues. There can be multiple processes in waiting state. Third, from running state a process can move back to ready state in case the time slice of the running process expires or in some other situations. In this case, the CPU allocated to a running process is preempted, that means it is taken away by the operating system and the process enters the ready state and joins the ready queue. Whenever some event occurs in a system, a process executes and changes its state. The process of changing a state is called a state transition. The various state transitions include new to ready, ready to running, running to ready, running to terminated, running to waiting and waiting to ready state. The movement of various processes among these states has been shown in the process state transition diagram. Initially, a process P1 enters from new state to ready state and goes to running state as CPU is free. In the meantime, P2 enters ready state from new state. The time slice of P1 expires and it comes back to ready state. P2 goes to running state. Again, a new process P3 enters in ready state. The time slice of P2 expires and it comes back to ready state, and P1 goes to running state. When P1 requires some input output operation, it goes to waiting state and P3 comes to running state. In the meanwhile, P4 enters in ready state from new state and P3 comes back to ready state as its time slice expires. P2 goes to running state and P1 joins the ready queue in ready state after completing its input output operations. P2 goes to terminate state by executing itself to completion, and CPU is assigned to next process in ready queue. This process goes on. The operating system is responsible for managing all the processes that are running on a computer and allocated each process a certain amount of time to use the processor. In addition, the operating system also allocates various other resources that processes will need, such as computer memory or disks. To keep track of the state of all the processes, the operating system maintains a table known as the process table. Inside this table, every process is listed along with the resources the processes are using and the current state of the process. As we said above, a process is simply a running program. At any instant in time, we can summarize a process by taking an inventory of different pieces of the system it accesses or affects during the course of its execution. A process consists of at least an address space, the code for running program, the data for running program, an execution stack and stack pointer, SP, which traces state of procedure calls made, the program counter indicating the next instruction, general purpose processor registers and their values, a set of operating system resources like open files, network connections, sound channels. In other words, it is all the stuff you need to run the program or to restart it if it is interrupted at some point. All this information related to some process is stored in process control block as discussed below. Process control block. Each process is represented in the operating system by a data structure called process control block or PCB, also called process descriptor. A PCB contains all information pertaining to a process that is used in controlling its operations as shown in figure. When a process is created, its PCB is also created by operating system and the same PCB is deleted when process terminates. The contents of PCB contains following information. First is process state. It contains the current state of the process, which may be new, ready, running, waiting or terminated. Next is program counter or PC. PC contains the address of next instruction to be executed for this process. Next, CPU registers. CPU registers like accumulators, index registers, stack pointers, general purpose registers, etc. are required to hold the data to be processed and also holds intermediate results. Whenever CPU switches from one process to another, the contents of these registers are stored so that process can resumed correctly later on. Next is CPU scheduling information. It contains process priority, pointer to scheduling queues and any other scheduling parameters are stored here. Next is memory management information. It includes address of the memory area and memory units allocated to process. Also, the values of base and limit registers are stored here. Next is accounting information. It includes amount of CPU and real time used, secondary storage used, time spent in waiting for input output completion. Input output status information. This part includes list of input output devices allocated to this process, a list of open files, etc. Next is process ID. This is the unique number assigned to each process at the time of creation of process. Next we have system view of the resources. As we have already discussed that during lifetime of a process, it uses many resources to accomplish its tasks. There are two ways to share or multiplex a resource. First is time multiplexing, where users take turns in using the resource, for example processor, and second is space multiplexing, where users occupy different parts of the resource simultaneously, for example main memory. The processor is an exclusive or dedicated resource. That means it cannot be used by two processes at a time. When an exclusive resource is allocated to a process, the resource is said to be busy or occupied. Any other process that needs the resource must wait until the resource becomes free or available. The operating system must keep track of which processes are using which resources so that it can manage both resources and processes effectively and fairly. We use the term allocation to denote a reservation of a resource by a process. Every resource, either exclusive or otherwise in the system, is managed by a program piece called an allocator. Allocators of resources are part of the operating system. A process interacts with an allocator to acquire and release the resources managed by the allocator. Resource sharing or resource multiplexing is a vital activity in a computer system to improve resource utilization as well as system performance. However, the sharing leads to competition among processes for the resources. The operating system has to ensure that the sharing proceeds smoothly and amicably. When there is more than one process waiting for a busy resource and the resource becomes free, the resource allocator is required to make a decision in finite time of the order the waiting processes will get the resource. To allocate the resource to these competing processes, the allocator follows a set of decision rules called the allocation algorithm or scheduling algorithm. When executed, a scheduling algorithm may take into account various process dependent parameters to select a process for the allocation of the resource. The allocator is expected to provide service that is acceptable overall to the processes. For example, the processor scheduler may allocate the processor to the processes based on their priorities in the order of their creation or first come first serve basis. If a request for a resource cannot be granted to a process immediately, the process is put to wait in a queue associated with the resource called a waiting queue. Later on, when the resource becomes free, it is allocated to the most deserving process from the queue. The selected process is removed from the queue, awakened and allowed to use the resource. We say the process has reserved the resource. The operating system reclaims a resource when the owner process no longer requires it. Next topic is initiating the operating system. At the very beginning of system bootstrapping, for a limited period of time, there is no operating system or a process in the system. The processor executes a bootstrap program from the boot ROM, first brings a portion of the operating system into the main memory and then executes operating system programs. In this initial phase of bootstrapping, the processor executes operating system programs, though not in the context of any process. The operating system initializes various data structures and creates a few kernel and user processes. In the midst or at the end of the bootstrapping, the execution control is transferred to a process. From then onwards, the processor always executes machine instructions on behalf of a single process, which can be a user or kernel process. Note that an operating system is not a process, but a collection of programs that the processes may execute. Finally, we have conclusions. Operating system views the processes as liability to complete using various assets it has. In operating system view of processes, operating system takes care of various characteristics of the process like creation of process, process state, current activity of the process, etc. It is the responsibility of operating system to take care of all the processes and providing them all the resources for their successful completion. Any process can be in one of the 5 states at any time. During its life, a process moves from one state to another. A PCB is associated with each process containing all the vital information about the process to execute it any time. Similarly, system views all the resources as its assets and uses these resources to provide the competing processes to run to completion. Thank you.